Last topic, speed, time, and velocity with the vector equation. So in 3 dimensions, vectors can be very useful in this application. So what have we already seen with the vector equation of a line? We've got a position vector of any point on the line. We've got a starting point. And in particular, because what we're going to start to see with applications to speed, time, and velocity, t is going to be a time after a starting point. So your vector A will be a position vector at time equals 0. This is where a particle, a thing, a car, an airplane, that's where it started. B is your direction vector, and you're multiplied by some scalar t, which we're going to find out will most likely be time. There we go. I got to go like this. And we're back to a regular size screen. Perfect. So like I said, now the things that are going to change is A is going to be a starting point. Your direction vector is going to be our velocity vector because it will tell us how far we go in 1 unit of time. And the length of our velocity vector will be the speed of the object that's moving. So we'll start off with a 2-dimensional question and sort of imagining that you're looking at something from above traveling on the ground. So we've got our vector equation. We've got a starting point, 1, -1. And the unit vectors, in this case, represent kilometers. So the 1 kilometer means 1 kilometer to the east, because that's your x. And the -1 on the bottom would be 1 kilometer to the south, because a +1 would be in your y direction to the north. And time is in hours. So the velocity vector is always your direction vector. And the length of your direction vector, a squared plus b squared, and since we're dealing in kilometers and time in hours, the length of your velocity vector will always be the speed that the object is traveling. So this object is traveling at 5 kilometers per hour. So for those of you that just got here, we are doing the application of the vector equation to speed, time, and velocity. The newest things are that your direction vector is your velocity vector. The length of your direction vector is the speed that the object is going. And t stands for time. So basically what this means, when we draw it out and sort of have it as understanding, okay, you would have the point 1, -1. So that point is on your line. Your direction vector is 3, 4. So that would mean 3 in the x direction and 4 in the y direction. And your equation of your line would mean that it continues along that way. Now, if you went 3 in your x direction and 4 in your y direction in 1 unit of time, because when t is 1, that's what's happening. You're going 3 to the right and 4 up. A squared plus b squared equals c squared would say that you're going 5 units in that time. Since the units are in kilometers and time is in hours, you've gone 5 kilometers in 1 hour. What's your speed? 5 kilometers an hour. Oh, have you ever seen the 80 kilometers an hour video? No, well, maybe at the end, if we have time. It's, yeah, okay. Describe the motion of the object in words. The object is moving at 5 kilometers an hour in the direction, and we can give the direction vector. So the reason that the direction vector is called the velocity vector is because velocity has a length and a direction, whereas speed is just a scalar. It's just telling you how fast something is going without necessarily giving its direction. Okay? So the object is moving at 5 kilometers per hour in the direction 3, 4. I guess technically you could say the object's velocity vector is 3, 4, and that would tell both of those things at once. How do we change something from a vector equation to this is y equals mx plus b rearranged? We have to take our vector equation of our line, which was 1, negative 1, change it to the parametric equation. So almost everything runs through the parametric equations, where your x coordinate is 1 plus 3t, your y coordinate is negative 1 plus 4t. And then to get the Cartesian form, you have to solve for t in both of them. So in equation 1, you can get t by itself by moving the 1 over and dividing by 3. In the second equation, you can get t by itself by adding 1 to both sides and then dividing by 4. So that would allow you to equate them. And now we have our Cartesian form. Now, according to what they were looking for ax plus by equals c. So we need to take the equation that we have and just do a little bit of rearranging. I can multiply both sides by the 4 and both sides by the 3 to get 4x minus 4 equals 3y plus 3. I put my x's and y's on the left side and my numbers on the right side. I've now rearranged it to match the form that they were looking for. Okay, this one too is not enough? Thank you. Yeah, that one's terrible. Yes. Yeah, and it was at the bottom there. Fair enough, thank you. So again, this one is a two-dimensional question. If we want the vector equation of the line, we have a starting point. With our x, it's 4, and with our y, it's 5. And our direction vector, with the x, it was 5, and with the y, minus 2. Two-dimensional vectors, as far as applications for those are really good for objects traveling on water. Because boats that are on water, it's basically flat. It's not very like, oh, I hated going on that uphill part of the lake. That doesn't happen very often. And so two-dimensionals work very well for that. Maybe Manitoba and Saskatchewan on land, we could say it's flat enough that we could use two-dimensionals. But as soon as you go to more hilly spots, or as soon as you go to air travel where you don't have to stay in the same flat part, then we're going to be going to 3 dimensions. So we got a moving object described by this. Maybe it's a boat on water. Write down the velocity vector. Well, the velocity vector is your direction vector. And to calculate the speed, We find the length of our velocity vector. Time is measured in seconds and distance in meters. So our speed is root 29 meters per second. And then this is a very typical kind of application. We've got our equation of our line, we've got our speed, we have our direction. There is some object that could cause harm to this boat. Happens to be a big pole in the middle of the lake, not sure why. Okay, maybe a lighthouse. Maybe the pole is on a rock that is, maybe it's not a boat. Maybe it's just some child running in a park. Have you ever run into a pole? Only once. That's another story. Okay, so I'll tell you the pole running into story after this. If this is the case, we have our equation of our line, we have our parametric equations. Our parametric equations were 4 plus 5t, and we have y equals 5 minus 2t. If you plug in the point, then you would have 39 for x, and you would have negative 9 for y. Can you see a little bit of mental math here? Move the 4 over, divide by 5. This would happen when t is 7. And a little bit of mental math here. Move the 5 over, divide by negative 2. Since t is equal to 7 for both of them, okay? This means at 7 seconds, the object will collide with the pole. Yes? You could use Cartesian form as well. You can use any of the forms. I like to use the parametric forms because there's so many applications for it. But what it's basically saying, if you have the Cartesian form and you plug in 39 for x, you should get negative 9 for y. If it works, then you know that that point is on the line. If it doesn't work, then you know the point is not on the line. Yeah, when, if it's asking also when does it hit, this is more useful. Because not only does it tell us it hits, it also gives us that information of when it hits. Okay. Walking into a pole story for me was grade 6. In grade 6, our school, my elementary school, decided on a great plan. I guess we were not very productive or we were too off the wall, not sure. But they made a whole school plan that every Wednesday afternoon we would not have any formal school. We would just get to choose an activity and do that activity for the whole afternoon. Activities included woodworking projects with popsicle sticks, baking. That's where I realized that if your mom measures out the exact amount of sugar for both the crust and the inside of your banana cream pie, and you use all the sugar first in the crust, and realize you also needed sugar for the filling, and got the exact same amount again, and put it all in the filling, that your banana cream pie is way, way too sweet. But that has nothing to do with the pole. The pole happens to have to do with when I chose bowling for my activity. And while choosing bowling one time in grade 6, there I was, game was starting, and I bowled a strike to start. And I thought, oh, this is exciting. Then the second round came up, and I bowled a strike again. And the third round, a strike again, and the fourth and the fifth, until I had 7 strikes in a row to start off my game of bowling. Okay, prior to this, I don't know if there's bowlers out there, but I think my best score ever was like 105 in 5-pin bowling, and now I had just started off with 7 strikes in a row. I ended up with 303 points in that game in lane 3, so the number 3 was my favorite for at least a couple of years. Happened to be the highest score in the small town of Rostron for the entire week, and won a case of 6 750 ml Pepsis, which I cherished very much. And on the way home, I was walking with friends saying, I can't believe, I had my head down and I was shaking my head saying, I can't believe I bowled 303, and I walked straight into a road sign. I've never bowled that good since. It was a blip in time, and that's my walking into a pole story that connects to this one. So jet is flying at a speed of 700 kilometers per hour in this direction. But this direction, if I find the length of 2, 6, and -3, it would be 4 plus 36 plus 9 is not equal to 700. So we need to have this same direction, but we need it so that a squared plus b squared plus c squared, when we add them up and square root it, it's equal to 700. Okay? So what's a strategy for doing this? If we find out, well, we could find out what this length is and multiply by some sort of factor. That could work. Probably the easiest way is to start with the unit vector. If I add these together, I get 7. So does it make sense that the unit vector is 1/7 of 2, 6, and -3? And that would have a length of 1. Now this is probably one that you could have done mental math otherwise, right? You could probably say, well, if this has a length of 7, what would I need to multiply it by to get a length of 700? I would need to multiply by 100. Okay? But there's sometimes that this number here isn't an easy multiple. And so finding the unit vector is nice, because then you just have to multiply your unit vector by 700 to get your velocity vector to have a length of 700. Okay. A yacht leaves a harbor. Ooh, it's a sanctioned yacht, so we're after it. This is a good boat on the water question, right? leaves a harbor at time t hours given by this vector, xy equals t58. Okay, so can you see that the harbor is position 0, 0 in this case? There's a cargo ship, and its position is given by xy equals 63 plus 37. Okay, distances here are time is hours and k is kilometers. Find the speed of the yacht. So we need to find the length of which vector? The direction vector. So the length of 5/8 will be 25 plus 64 is the square root of 89 kilometers per hour. I don't know, I'm not a drive a lot of boat kind of person. That doesn't seem like a very fast traveling boat. 9 kilometers per hour? Okay. Yeah, I guess you're just traveling. You don't want to be going too fast in the harbor.
Yeah, most of them, most harbors have a maximum speed of, it's definitely under 30 kilometers an hour.
Okay, so it's not so bad.
And I know that residential lakes in Manitoba, at least, it's 15 kilometers an hour here, 30 kilometers an hour there, and it's usually not recommended to go too fast.
So, what is the distance of the cargo ship from the harbor when the pleasure boat, the yacht, starts its journey? So that would be at time equals 0. Where's the cargo ship? Well, we can put in 0 for t into the cargo ship's equation, and we would be at 6,3. How far is 6,3 from 0, 0? Again, you're looking at just finding the distance from 0, 0 to 6,3 would be the length of that vector. Square root of 45. That's how many kilometers it is away from the harbor. Okay. There's going to be a bit of a theme, just warning you about these notes. So you have things traveling on vectors. The theme is, will they run into each other or not? Okay? They're going to continue on their same courses. Will they collide? In other words, how do we use our vector equation of a line to find out if there's an intersection point? We look at the parametric equations. So and I'll look here, I've got my notes right here. If we go to the yacht's equation is 5t and y equals 8t. The cargo ships got 6 plus 3t and 3 plus 7t. So one thing that's a little bit different compared to the questions we were doing before. When we were doing them before, we had two equations with two different parameters. The first equation had a t, the second equation had an s. Because they're not necessarily on the same thing, and then you'd have a systems of equations which you had to solve. But in an application question, the time is the same. So as long as you have a reference point of that time, now we have, from our first equation, 5t equals 6 plus 3t, and in our second equation, we have 8t equals 3 plus 7t. Doing a little bit of mental math there, we can solve in the first equation that t has to be 3. Can you see that the second equation is the same? If you got a different t value for those equations, then they wouldn't intersect. What it would mean is they would cross the same point, but at different times. And as far as being on a lake, that's okay. It's just bad when you cross the same point at the same time. That's when you have a collision. So we now know I did write hours, yeah. Yes, we do need our units. So because the time equals 3 hours, at 3 hours, they will be exactly at the same spot. We could put 3 into the equation and find out that it would be 15 kilometers in the x direction, 24 kilometers in the y direction. That will be the point where the two boats would collide. And I would guess the cargo ship would win. Not sure, but they don't. Have you ever been to a demolition derby for cars? Where they have old cars and they basically, you drive around and crash into each other until cars don't work anymore, and then they are out. Is there such a thing for boats? Where you drive your boat around into other people's boats and then they sink?
I think there's some problems with that because you actually have to be physically on the boat to drive it.
Yeah?
It's a little bit different. You have to be in the car sometimes because you know there's safety factors.
Maybe. Yeah, you don't drown.
The debris can be managed.
You don't have to clean up. It just goes to the bottom. Ooh, some problems with that, eh? It's in the video. All right. We'll start it. First ever demolition boat derby coming up.
By the way, 400 on your notes is weird. This example starts about an inch down the page, not
I know. It's this. Yeah. I'm going to fix it up. Well, and the part of the problem with this, I would have switched it to the vertical notes, but then the original where I had included the vectors with cross product was missing. So then it was like, ugh. Okay. All right. So we got vectors, another two-dimensional one, another boat question. So here is a lighthouse is at 0, 0. And it can see in a radius of 25 kilometers. So anytime your boat is outside of that 25 kilometers, you cannot see the lighthouse. A ship is initially at point P, 31 kilometers west and 32 kilometers south. So this should be at about, there's where P should be. 31 kilometers west and 32 kilometers south. The ship is moving parallel to the vector 4, 3. So this means it's moving 4 in the x direction, which would be to the east, and 3 up, which would be to the north. Question?
On the test or quiz, they use directions like west and south. Should we assume that up in the y-axis is
North, yes.
and
Yeah.
to the right on the x-axis is east? So we should
Yes.
assume that it's
Yeah.
compass rose?
Yeah. Oh, okay. Shoot.
Lower and like right
There
there.
we go. Okay. So we're starting at point P. It's traveling at 20 kilometers per hour. And an hour after leaving, it's at point R. So if we imagine this, it's going to go 4 to the right and 3 up. Maybe somewhere there would be point R, going 4 in this direction and 3 in this direction. No, that's not true. That's a lie. Because if I go 4 in that direction and 3 up, then what's my length? 5. And then that would be a speed of 5. But we're told it's going in this direction with a speed of 20. In other words, it would have to be 4 times longer. Okay? So first of all, it wants us to write down O to P. O to P would be 31 kilometers west, which is minus 31, and 32 kilometers south, which would be minus 32. Show that the path of the ship can be represented by this equation. In order to show this, we need to find the velocity vector. Okay? It's not okay just to show that this equation works. We actually have to derive it. We already know the starting point is negative 31, negative 32. So that point is okay. We need to find the velocity vector. The velocity vector, we're told that it goes in the direction of 3, 4, or 4, 3? 4, 3. And the length of 4, 3 is 5. Okay? Since our speed is 20 kilometers per hour, we would need to multiply by 4. So if you take 4, 3 and multiply by 4, you get 1612 as your velocity vector. Therefore, your equation of your line is your starting point, negative 32, negative 31. Whoops. Negative 31, negative 32. Plus time and 1612. Okay? So going back to our diagram. We've got P. We've got R. In 1 hour, does it make sense that this would be 20 kilometers difference in between them? If we want to find OR and PR, okay, we need to find out where R is. Right? And the point R occurs when time is equal to 1. So if we go to our vector equation, 31, and we plug this in, we will get negative 15, negative 20. So OR is equal to negative 15, negative 20. what is P to R? Okay. Well, you could either, right, if you want to figure out P to R, and we already know the position vector for O. Can you see that if you wanted to use your vectors, if I want to go from P to R, I could go from P to O and then O to R. That would be a visual direction of this. So if I'm going from P to O and then from O to R, since O to P is negative 31, negative 32, P to O would be the negative of that, plus O to R, negative 15, negative 20. And when we simplify this, you get your direction vector that we had, which should make sense because all P to R was how much you've traveled in 1 unit of time, which is exactly your direction vector. So you could either solve this by looking at the points, or you could have, if you wanted to just logically say, I know that this would be the direction vector, that would be fine as well. Show that when the ship reaches R, the lighthouse first becomes visible. So if we find the length of OR, it would have to be 25 kilometers because that's how much that's when you could see the lighthouse. So if we find the length of, what was it, negative 20, negative 15? Man, I've been flipping them. Thank you. Negative 15, negative 20, which will be square root of 225 plus 400 which is 25. So since the lighthouse is visible at 25 kilometers, point R is the first time it becomes visible. And of course, to stay with the theme,
I think whoever wrote these notes really likes large, fatalistic accents.
sorry.
And explosions and or violence between objects. It's a little bit concerning.
I'm sorry. Okay, well, maybe this one has a better outcome. It doesn't. Do you need to go back? You're good. A second ship's path can be described by the following vector equation. Determine if the boats will collide. Explain your answer. So again, we'll look at the parametric equations. First one is of the first boat, which is negative 31 plus 16t, and negative 32 plus 12t. The second boat's parametric equations would be x equals negative 7 plus 10t, and y equals 4 plus 3t, which gives us the following equations. Negative 31 plus 16t is equal to negative 7 plus 10t, and negative 32 plus 12t is equal to 4 plus 3t. Is that too much mental math? Can you do that one in your head? T is equal to? I got 4 for the first one. How do you do? And the second one? Oh my goodness. Unbelievable. What is our units here? Hours? Yes, it is hours. Yep. I get 90 on this side and 36 on that side. Add 32. This really should be a better example where you made a mistake and the boats don't collide. It should really be, it should be that if we make mistakes, boats collide. And if we do our math right, everybody has good endings. But
I accidentally put an extra negative beside 4 because it's drawing an equal sign and I didn't.
so at t equals 4 hours, the boats would collide. I should really include a 3-dimensional one because it's not hard. But it's the same thing, except you have 3 equations where the t all has to be the same. We could have a riveting example of a flying squirrel and a bird. And will they collide?